Alright, so we're going to enter into the gaseous state here, and this is a little background information, talk a little bit about kinetic molecular theory, and also pressure and some pressure units and conversions. Now, the AP exam typically does have a decent amount of gas questions on there. A lot of them will focus on equilibrium, which we'll study later, but several questions do come straight from like the empirical gas formulas, where we're just comparing a couple different variables. But first off, it is important to remember that gases are compressible. All right, so when we apply pressure to a gas, we get the molecules to move closer together. And if we apply enough pressure, yes, we start to change the volume, we decrease the volume, but eventually the intermolecular forces of attraction will take over, pull the particles together, and you'll get the gas to turn into a liquid. And that's pretty important, especially, storing gases. Like if you go to the store and get some Hello Kitty balloons, the helium tank is there. It's under tremendous pressure, and you just open it up and get a little bit out that you need. It expands into the balloon, and life is good. The other important thing to remember is that gas-particle collisions create pressure. And this wasn't always the truth, or I'm sorry, not always the belief, and we'll talk about that in a little bit. But pressure is by far one of the more important variables that we discuss when we're talking about the gaseous state. So when looking at pressure, there's two main instruments that are used to measure. First, we've got a barometer, and second, we have a manometer. I apologize if I mispronounce that, but that's how I say it. Our barometers measure the pressure of the atmosphere. Our manometers measure the pressure of a gas or a liquid that's in a vessel, so more like in a chemistry lab. Now, obviously, our barometers don't look like this picture anymore, but this is what they looked like back in the day. Okay, and we've got this pool of mercury, and the atmosphere pushes down on it, and the mercury rises up into the tube. So if you take this barometer, put it at sea level, then the mercury would rise 760 millimeters up into the tube. 29.92 inches is what we see there. So when you hear the weather forecast and they're talking about the barometric pressure, when it's 30 inches or above, we have a high pressure hanging over our area and we have nice weather, clear skies, sunny. When the pressure drops, that's when the bad weather moves in, when we get a low pressure front coming in, and so we'll experience worse weather. The SI unit for pressure is the Pascal, all right, kilogram per meter second squared. Basically, it's what is 1 Newton of force being applied on 1 square meter. And so that's how that ties in there as far as our SI units are concerned. The problem with the Pascal, it's pretty small. Okay, so typically in chemistry class, we will not use that. 1 atmosphere is 101,325 pascals. So our typical standard 1 atmosphere of pressure, it's a lot of pascals. So if we do use pascals, typically we'll use kilopascals. And it said 1 atmosphere is about 101.3 kilopascals. I did just mention that 1 atmosphere of pressure makes the mercury rise 760 millimeters. These millimeters of mercury are also called the torr, in honor of Mr. Torricelli, who developed our barometer. And there has been a push lately to get the bar to be used. You can see the tie-in between the bar and the Pascal. An atmosphere and a bar are very, very close, but as our textbook even mentions, until something major comes along and they demand that we use the bar, we pretty much stick with the atmosphere when we're doing a lot of these chemistry problems. But oftentimes we need to convert between these units. So here it says a gas in a flask has a measured pressure of 797.7 millimeters of mercury. What is this pressure in kilopascals and atmospheres? All right, well, the first thing we know is that there are 760 millimeters of mercury in 1 atmosphere. So that conversion gets us to 1.050 atmospheres. If I want kilopascals, then I just carry that out because there's 101.3 kilopascals per atmosphere, so that ends up at about 106.3 kilopascals. Okay, so again, there might be times where you have to convert between these units, And you can use any of this information provided in order to do so. And a lot of this is on your AP equation sheet, so you don't even have to memorize that. So our last thing here is the kinetic molecular theory, or just kinetic theory of gases. All in all, mainly we're saying that a gas consists of molecules that are in constant random motion. Now back in the day, Sir Isaac Newton, he talked about gas pressure coming from the fact that gas molecules repelled each other. And so we know that not to be true anymore, but for a long time people say, hey, that's Sir Isaac Newton, we believe him. And even though people had mathematical and experimental proof otherwise, saying that no, it's the collisions between the particles, it was put on hold for a while, and it took quite a bit until we finally believed these new theories. Alright, so again, currently we say that pressure results from continual bombardment of the container walls by moving particles. And this was back about the late 1800s that the kinetic theory took over. So depending on what book you might look at, there's 4 or 5 postulates that kind of come together and make this theory. But essentially, summed up, it says gas molecules are small, and their volumes can be ignored, so most of the volume of a gas is empty space. If you're in a large room and you take all of the gas molecules and put them together, they might combine to be a volume of about that. Compared to the whole room, that's not much. So oftentimes we just say that the volume due to the gas particles is negligible, can be ignored. These molecules move in straight lines, in all directions, at various speeds, with no intermolecular forces at play, meaning there's no senses of attraction between these molecules. And that's true until they collide, but also, like we were talking about, if we increase the pressure so much that these molecules now come in contact with each other, the intermolecular forces will take over and cause the gas to become a liquid. That can also be accomplished if we'll talk about that later. Now, if these particles do collide, they will collide elastically. And that means all the energy that goes in comes out. The total energy is constant. And then the last part here, the average kinetic energy of the molecules is proportional to the absolute temperature. And of course, remember which scale that we like to use with our gas laws and whatnot, Kelvin. Because what is 0 Kelvin? Absolute zero. And so at absolute zero, there's no more kinetic energy of particles. And so we like to use that temperature scale to talk about these gas laws and the mathematical relationships because it's a direct reflection of the kinetic energy of these molecules. All in all, the best thing that comes out of the kinetic theory will end up being the ideal gas law, PV-NRT, PV equals nRT. But there are real gas scenarios. Not all gases behave ideally, so we'll see an adjustment to that later on. But essentially, we can qualitatively analyze the kinetic molecular theory, and it all came from these empirical gas laws and people working with it. So like Mr. Boyle, he was looking at some containers of gas. All right, and here we see as volume increases, pressure decreases, and vice versa. As the volume decreases, pressure increases, an inverse relationship. And so the important thing to remember about this is that while he was discussing and measuring pressure-volume relationships, there's other factors involved. The amount of gas, which we typically talk about in moles, is constant, as is the temperature in this scenario. So those two are constant while he was checking out the pressure-volume relationship. Over here, 2 liters of a gas at 300 Kelvin. If the temperature goes up to 600 Kelvin, we have 4 liters of gas. So there we're looking at a volume-temperature relationship. That's Mr. Charles. And you'll notice here, isobaric and constant moles. So constant amount and isobaric means the same pressure. Okay, isobaric, like an isobaric chamber. Here's another important one. Here I have helium and nitrogen and methane. Same volumes, same pressures, same temperature, same number of gas molecules. This was courtesy of Mr. Avogadro. And so we see a very important fact here that at the same temperature and pressure conditions, 1 atmosphere and 0 degrees Celsius, we typically call that STP, standard temperature and pressure, any gas will have the same number that has the same number of particles will have the same volume. Different masses, okay, we realize that courtesy of our molar masses, so they have different densities as well, since the volume's the same. But we'll see that very important fact. And you know, think about the obvious. The greater the amount of gas put into the balloon, then the larger it will become. So there's a direct relationship there between more particles, larger volume. All right, so that just kind of goes over some of the thinking that we'll be encountering. Remember, you're going to be presenting a lot of the information for this chapter for us, so that'll be good. And I'll be back to help with some gas stoichiometry, some real gas behavior, as well as the collection of gas over water and partial pressures, which we'll need in order to do a lab that we have coming up. All right, hope this introduction helps you, and I'll see you soon.